I think so.
Hi,
the
everybody.
timer's on.
Welcome to this coffee talk. We're going to talk about whether we do need to wait for quantum computing or whether we've got some solutions to our technology problems now. I'm Alastair Cooke. I organise the V Brown Bag podcast and all of the V Brown Bag community technical education content. And I'm somewhat qualified to sit on the stage with Ray, having done a physics degree in the very deep, distant past and never used it for anything useful. Joining me on the stage is Dr. Ray.
It is Dr. Ray.
Dr. Ray Beausoleil. Sorry, I'm also mangling your name. Ray, would you introduce yourself quickly?
Sure. I'm a senior fellow at Hewlett Packard Enterprise, and I lead the most important aspect of my job there is to lead a group that we have called Large-Scale Integrated Photonics for a decade now. And we work in photonic interconnects, optical computing, and we're moving into a new field of flexible hybrid electronics, and eventually photonics, because I'm too lazy to change the name of the group.
So you have to eventually hit the
Eventually we have to have flexible photonics as well.
So setting the stage, what are the sorts of problems we're seeing customers facing at the moment that we really need to address and that maybe quantum computers will help us with eventually?
Well, in the enterprise, our most pressing problem is trying to gather from hither, thither, and yon all of the data being generated at the edge, sometimes being stored in the cloud, sometimes being brought in to enterprise-scale private data centers. And we've reached a point where these data sets have become so large that our old approach to memory, which was memory attached to compute and put on a board, and then you can slip those boards in and out of servers, it just doesn't work anymore. And it doesn't work in data centers or in high-performance computers. And so we've moved to a different paradigm, memory-driven computing, that we're using as a platform that we can innovate on. And we start with memory-driven computing. We have technologies like Gen Z that make it easy to address and access memory, large shared pools of memory. And we want to take advantage of that then to attach other computing elements that we can use to solve really hard problems when the current CMOS, the silicon, is really not up to the job.
So part of the problem is that the scale of data that we're working with is too large for a single x86 computer to handle.
It's gotten crazy. If you look at the data sets just generated by a small fleet of self-driving cars, it was originally estimated to be a petabit, in other words, 1,000 trillion bits a day, and it's moving to 1,000 trillion bits per hour. It'll eventually be even larger than that. And the problem is that this isn't being generated inside of a building. It's being generated out at the edge, where the Internet of Things is gasping for air, hoping that it can handle that data and do something useful with it. And so having a computational paradigm that allows you to start addressing these enormous data sets, there's a lot of IP in this data, and our customers are desperate to process it in a way that benefits their mission.
And the conventional way to deal with very large amounts of data is to take lots and lots of computers, lots and lots of x86 machines, and attach them to a network. And
Correct.
We're getting to the point where that network is so much of a constraint on moving the data.
Correct. And so
we need a different way to do this.
You're exactly right. And so being able to put all of that data into a very large shared memory pool, and then making it easy for compute, no matter where it is, to access that data and use it is, I think, the next paradigm, the next generation of compute.
And this is continuing on from the work that we've seen with the machine over time.
Exactly.
And what we've seen announced yesterday with the sandbox on I'm blanking the name of the product now.
Well, the sandbox is so new, we aren't sure what to call it yet.
But this is allowing us to do the in-memory compute, the large memory fabrics, the 160 terabyte of RAM as a single address space.
Yeah, and in fact, so what's neat to me about memory-driven computing is that you stop trying to shuttle data everywhere, because you have a lot more of that than you do, the size of the programs analyzing the data are not that large, and it's much more efficient to load your network up with the compute and send the compute to where the data is. And so, you're flipping 40 years of computing algorithms and technologies on its head, and I think the future looks really bright.
And in that future is the storage class memory where that large fabric of currently RAM transitions to being a persistent storage, and so you don't need to back the data out to somewhere else.
That's right. It really does call for eventually non-volatile memory, and we have hybrid systems now that act like non-volatile memory, to be followed by genuinely non-volatile memory technology. But if you can get to a point where you can treat the memory that contains the data that you are using to mine for information also into the hard drive that's storing it, then it's win-win.
And one of the really interesting things we saw last year in the Blogger Coffee Talks, which you can find on YouTube on the Geekazine channel, is the dot product engine using memristor technology in order to essentially offload what is, for an x86 computer, a really hard piece of work to do a matrix multiply. Can you talk a little bit about what that is and some of the other sort of acceleration technologies that the labs team have been working on?
Yeah, and it's actually useful to think of a quantum computer as an accelerator for a certain type of problem. We are also in parallel working on optical computing for solving certain types of optimization problems, but the neat thing about the dot product engine is that if the compute requires a huge amount of matrix vector multiplication, which is the bread and butter of deep learning systems, deep neural networks, you can almost hear your x86 computer creaking under the strain when it has to do that at scale. And so being able to offload it to a machine that not only can do it more efficiently because it's inspired by what we believe to be the architecture of the brain, it also can do it in parallel. And so you get intrinsic parallelism in a compute element that is more profoundly efficient than what you get if you farm out a whole bunch of different calculations to cores. See, using multiple cores to do things in parallel is our conventional understanding of parallelism, but it's cheating. You're using multiple computers to do calculations at the same time. If, on the other hand, you're using something like the dot product engine, it is as if you can do parallel computations within one core. And so the DPE is an excellent example of an accelerator that we can harness whenever we've got any kind of numerically intensive matrix vector multiplication, and deep neural nets are just one example of an application that requires that.
And that's this trend that I'm seeing to offloading specific tasks from the x86 processor to something else. We see it quite a lot with the use of GPUs, and we see it also increasingly with FPGAs, and now we're seeing other types of accelerators.
And one of the reasons that I love memory-driven compute is that instead of lighting up an accelerator and saying, okay, it's now the compute is in your hands, and then shipping all the data over to the accelerator, instead you just say, hey, go look over here at this particular memory address and do what you do and do it well, and then let me know when you're done, and then I can go to the same memory location and grab the result. And so if you're a scientist and you're doing research, then having a platform like that is a godsend because it makes it much easier to innovate. You don't have to do everything soup to nuts. You can literally just build an accelerator for particular types of problems, confident that you'll have access to the data and you won't actually have to provide this high bandwidth connection and copy data from one place to another.
Now, we started the title here with quantum computing as being the draw, and it's getting a fair amount of press, and particularly the usual new technology is going to break old technology. What's the reality of the state of quantum computing?
That is a very deep question. What is reality on quantum computing? Let's take a step back and just ask, what is the reality on classical computing? We'll start there. So if, like it or not, you're using, or whether you're aware of it or not, you're using quantum technology now. The transistors in your laptop, in your phone, in your tablet, those transistors are modeled using quantum mechanics. And so in classical computers, we harness quantum mechanics where we can, and then we suppress it to reduce the effects of quantum mechanics, the harmful effects on our ability to do classical computing. And so in the case of quantum computing, we not only don't suppress those quantum effects, we harness them as well. And so this is where you hear about coherence and you hear about entanglement and all this other really fancy stuff. And we've been looking for quantum computation to become a thing for 70 years. That's when Richard Feynman first proposed the idea. And the types of problems that quantum computers are really suited for, that they're perfect for, are questions that are very simple to state, that have very simple answers, but the intermediate computation is so complicated and so complex that you'd have to wait essentially forever for your x86 computer or even a memory-driven computer using ordinary classical technology to finish. And so eventually what you want to be able to do is use a quantum computer in particular to simulate other quantum systems. And so for example, what's the next material beyond silicon that will inspire the next Moore's law? What kind of medications or drugs or other biological problems can we solve if we understand how to properly model the molecules that are the foundation of those new medical technologies? And so quantum computers are absolutely ideal for that. It's a very exciting time, and enough progress has been made over the last 20 years in scaling up the number of qubits, quantum bits, that we can use to do those calculations, that we're seeing all the excitement in the press. Now, to get to your, so that's a very large way of avoiding your question, which is what is the current state of the art? And the truth is that the qubits that we have on offer right now are in fact quite noisy. So in fact, they're generally, it's very hard to do a robust long-term calculation with high probability of success with the qubits we have available now. And over the course of time, as we get more and more and more of those qubits, we can use them together to execute algorithms that are called quantum error correction, which are quantum versions of the error correction algorithms that you already have in all of your CMOS and all of the silicon that you've got inside your phone, your tablet, etc. And right now, roughly speaking, Professor John Preskill at Caltech gave a keynote address at a Quantum for Business conference last December, and in that, in the manuscript that I saw from that keynote address, he was estimating that right now, if you wanted to build one reliable qubit, you'd need about 1,000 of the qubits that we currently have on offer that are in fact quite noisy.
So it sounds like we need some significant innovation before we'll be doing a significant amount of compute using these quantum
you know, the real question is the way we'll know quantum computing is a thing, a reality, is when we can use one to teach us something we didn't already know. And it should be an important question that we're trying to answer. And I think that we will, you're absolutely right, there will be significant innovation. We haven't talked about, we never talk about quantum gates and how reliable they are. They're the actual, that's the technology that actually takes your quantum bits and manipulates them to eventually deliver a particular result from the quantum computer. So we're going to need a much higher level of noise control in both the qubits and the gates than we currently have.
And so I can't expect in the next couple of years to have a quantum laptop that's going to run Excel so much faster than my current laptop.
And you know what? Running Excel is probably the worst application I can think of for a quantum computer. So quantum computers are amazingly good at simulating other quantum systems, or we hope they will be. They should be. There's every reason to believe they will be. But they're really terrible at the 3 R's, reading, writing, and arithmetic. We don't actually know how to take a big database and encode it in quantum bits and then work on it. At the current time, and in fact, so now, I won't go to the whiteboard yet, but if we want to take a petabit of information under ideal circumstances, we could write that petabit onto only 50 qubits. That's one of the things that are amazing about the way the quantum complexity scales. So Every factor of 1,000 is just 10 qubits, but those are 10 noise-free, perfect qubits, right? The problem is, at this point in time, we have no idea, really, how to efficiently take a petabit of information and encode it on 50 qubits. That's an unsolved problem. And nature is twice cruel. There's no such thing as a quantum hard drive. So you can't take your petabit database and then write it onto in a quantum form and then keep reading that database ready to go. Every time you analyze your quantum, every time you want to analyze your data with a quantum computer, you have to do that conversion over and over and over again. So there's something you don't quite know how to do, and I generally, if I don't know how to do something, I've learned at my age not to assume it's easy. So first we have to do that encoding, and we have to do it every time. And then the quantum computer goes ahead and builds out, for example, your neural network, if that's what you're trying to study. But then at the output, you learn that quantum computing has another issue, and that is if I have 50 qubits and I go ahead and I read my quantum register, I'll get 50 classical bits of information. And if you're building out a deep neural net that you want to embed on your phone, you want to take it online and use it to actually solve problems, that 50 bits is about one weight. And if you have so let's say a 200-layer neural net with 50 nodes per layer, that means you're going to have about 500,000 weights. And so you have to tailor your measurement to pluck out the weight you want, and then you have to re-encode your data into the quantum register, run the compute again, and get one more weight. You have to do it 500,000 times.
And this is related to the quantum effect, that if I observe a system, I change it, and therefore as I read that data out, I'm destroying the data as I read it out, essentially.
That's exactly right. And so the analogy that I like to use is a souffle. You know, we have absolutely no way to experience the quantum universe directly. That's why it's amazing that we discovered it. You know, there are clues in our part of the universe that tell us that something else is going on. And so over the last 100 years, we've discovered more and more about this quantum part of the universe. But our quantum computation has to be done in that other part of the universe, not in our part. And so to your point, you have to put your oven into the quantum part of the universe, put your experiment or your quantum computation into the oven, seal it up, and try to isolate it from our part of the universe. And if you do a really super good job of isolating it from our part of the universe, and you are patient enough that you don't peak. I mean, if you peak, the souffle collapses, your experiment doesn't complete. If you don't do a good enough job of closing the oven door, same thing happens. Even though you're not looking at it directly, the souffle falls. But even more amazingly, if you haven't done if you allow our universe to connect with the quantum universe even a little bit, something amazing happens. You put the ingredients in the oven, you program in the recipe for a cheese souffle, you're patient, you wait for the bell to ring, and you open the oven and out comes a chocolate souffle. And that's because this is the issue of quantum measurement. So ideally in a good quantum computer that's well isolated from our part of the universe, the answer that you want to get is very, very likely to come out of the computer, but there's no guarantee because every measurement that you make of a quantum system is probabilistic. So you have 90% probability you get the answer you want, or 90% probability you'll get a cheese souffle. Still, 10% of the time it'll be a chocolate souffle.
And this is why we need to parallelize out to deal with that statistic.
That's right, that's right. You should have 10 quantum computers going at all times.
Making 10 souffles.
That's right, so you get the souffle you want, instead of souffle surprise.
So given that the quantum computing stuff is probably a revolution in technology away from being business useful, let's circle back again to what is business useful in HPE's portfolio and development at the moment.
That's a great question. We actually had a quantum computing I had a quantum computing research effort going for quite some time, and about 6 years ago I ended it because I felt that it would be difficult to scale. I felt that running a compute accelerator that needed to be at essentially absolute zero, colder than space, outer space, was going to be inconvenient, particularly when you wanted to add it to your phone out on the edge. And instead, we began looking at enterprise scale problems and how we might be able to solve those. And our research has emphasized accelerators, and we've already talked about the dot product engine and how we'd like to use it to accelerate training deep neural nets. But in parallel, we've been looking at other types of problems, and computer scientists call very difficult to solve problems NP-hard. And the characteristic of an NP-hard problem is that as the problem gets more complicated, you get a wildly, incredibly increasing amount of memory and time that you need to get to the solution. And so we have been looking at a different approach, a coherent icing machine is what it's known as.
Google is not your friend when you're looking for information about that.
Yeah, I'm afraid not. I'm sorry. It's pretty new. But the idea is to use a model of a physical system. In our case, it's a simple model of a magnet that's made up of a bunch of mini magnets that the North Pole can either point up or down, and to use that approach to solve really hard optimization problems. And so a good example of that is the traveling salesman problem, where there are a number of cities that are separated by particular distances, and the idea is to find the most efficient path from one city to all the other cities. And as the number of cities increases, the problem just gets outrageously complicated, and it becomes essentially impossible to solve it on your laptop or even in a supercomputer. And so building accelerators that can handle those kinds of problems is a key part of the R&D mission that we have in my group, and in particular, and at labs in general, where the DPE is also being done.
And so what sort of business problems are you addressing with these tools?
I think if you look at supply chain management, if you look at, and that's down to the, from the global level of a company into an individual warehouse, you'd actually like to be able to solve these operational problems, these optimization problems on your phone if you could. At the warehouse level, just being able to do it on your phone and then load that information up into a global network is an ideal way to try to solve those problems. But there are other problems like operations in airlines, for example, and we know what bad operations look like.
We've all suffered from airline travel troubles.
And so being able to very rapidly, in just a few seconds, at the edge if necessary, use a room temperature system, so ours just operates at the same temperature we're at, to be able to use a room temperature computer to help solve the scheduling and optimization problems, to do supply chain management. Those are my favorite examples right now because they're essentially intractable at global scale.
But to be able to do the real-time calculation that if this particular weather event is shutting down a couple of airports,
Correct,
and aircraft
exactly.
aren't in the places we anticipate.
That's right.
And instead of taking weeks to recover from a weather event, then maybe...
Or even silly, ridiculous things as I've experienced, where your flight is delayed 6 hours because they haven't got the right bulb to replace the light in the bathroom. So crazy stuff like that ripples throughout the entire network of plane flights drives me crazy.
Yeah, I've only had an hour and a half waiting for the cover on one of the lights.
Yes, but we have all been there.
Yes. So we are about ready for opening the floor to questions. Do we have any questions out of the audience? Down the front here.
Hello, it's Uma Hassan from Computer Business Review in the UK. I know that you've mentioned upon quantum computing being quite complicated, but how can sort of enterprises sort of try and come on to sort of the quantum computing sort of trend, and how can they sort of try and prepare themselves in the best possible way to make sure that they are essentially ready for when the quantum computing sort of, when quantum computing sort of explodes, if you know what I mean?
I do. It really depends on the industry that you're in. It's a great question. I don't think we should regard quantum computing as a soup to nuts or end-to-end solution for our compute problems. It's an accelerator for certain types of problems. And so if you're in an industry that needs that type of problem solved, and if you're in pharmaceuticals, you're in material science, you're a semiconductor fabrication facility, you would love to have access to a quantum computer. And so if you regard, again, you don't need a quantum computer to run Excel spreadsheets for you. You don't. And so you can best be ready by understanding which of the problems that you want to solve in your enterprise would benefit from quantum computing, and then making sure that you're working with your suppliers to provide you with a platform that you can add that acceleration when it becomes available. So I don't think that you have to completely turn top to bottom your approach to compute. What you instead have to do is make sure that you understand what you need it for. You get away from the hype and you say, all right, what problems am I trying to solve? Will they benefit from quantum computation? Am I working with an enterprise company that will be able to harness a quantum computer as an accelerator, even if it's in the cloud when I need it? And those are the questions you should be asking. But you don't have to turn your IT portfolio upside down to get ready for it. It's not going to be that kind of technology.
Jim McGregor at Tirius Research. Thank you, first off, for saying more reasonable expectations about quantum computing. Several people are doing that now. It's not a panacea. But you have a lot of other technologies on the show floor, including neuromorphic computing, in-memory computing. A lot of these are going to play key roles in overcoming the limitations we have today, even new memory architectures and fabrication technologies. Can you maybe set some expectations as to where some of these various technologies are going to play, and what are the key technologies you see going forward to enable them?
That's a great question. So I think the first step is building out a different architecture, not only for compute, but also for networking. And so, the last few discoveries, we've been talking about photonic interconnects and collapsing the hierarchy of switches and data centers and all sorts of other. I could bore you for hours with this stuff because that's my bread and butter, photonic interconnect. But the first step, I think, is looking for systems with ever larger amounts of available memory just in the rack. And so we have tens of terabytes available right now in products that we ship. We're going to scale that from tens of terabytes to petabits over the next 5 years, and it's going to use shared memory pools. It'll use the memory architecture of the machine. It will use photonics to carry information from the compute to the memory. And those are the first steps. Once you have everything in memory and you can access everything in memory without having to shuttle that data all over the place, that's step one. Then step two, in parallel, we're working on one of the ones you didn't mention, well, you did, the neuromorphic computing, using brain-inspired, neuromorphic-inspired technologies to do a better job at what computers right now have trouble doing very well and in parallel, like just multiplying a matrix by a vector. That sounds like something that any computer should be amazingly good at, but in the case of a deep neural net, you do so much of it that it bogs down your ability to train the neural net, and you end up having to do the training completely offline, and it's very hard to update it with new data. And so, actually fielding a new version of voice recognition on your phone, it just seems to take forever. And so the first step to solving problems like that is adopt a new memory architecture, adopt new data center system-level architectures by, why do we need core switches and rack scale switches, top of rack switches? It's just crazy. With the kind of photonic interconnects that we'd like to field in 5 years, all the switches will look alike. And so I think those will have the biggest impact in the shortest term. NP-hard problems like traveling salesmen, supply chain, et cetera, that's for particular markets. Not all of our enterprise customers need to solve that problem, but we have people jumping up and down now for solutions like memory-driven computing and then the dot product engine, and that's what we'll try to field first.
Hi, Chet Houston with IEC. just sort of building off of one of the earlier questions about what organizations can do to get ready for quantum computing, you talked about some of the problems that quantum computing can potentially solve, but what about some of the security concerns of, a lot of security protocols are built off of like prime integer factorization, right? So does quantum computing then pose a risk to some of the existing security protocols that we have, and should organizations be looking at, potentially how to handle that sort of impact from quantum computing?
That is a great question, and I anticipated it by having a whiteboard brought to me. So let's figure out how to ask better questions when we hear claims made about the impact quantum computing will have on, name your problem of choice. Oh, awesome. The last time I did this on stage, there were no pens. We have pens now. This is a big advance. So let's use 2048-bit RSA crypto as an example. And we'll round down. We'll say it's 2,000 bits. So we start with a key that has 2,000 bits. Now, the most efficient circuit I have ever seen for implementing the Shor factoring algorithm that is supposed to crack that factoring problem needs about twice as many qubits, quantum bits. And 4,000 quantum bits sounds like, it's not that far off. We might have that in the not too distant future. There's a catch, as there always is with any new technology. Remember that number I told you earlier, that John Preskill estimates with the noisy qubits we have on offer today, we need about 1,000 of them to represent one good bit. So now let's do that arithmetic. And oh boy, what do we need? We need 4 million. That doesn't sound to me like something we're going to have in a few years. And so if you want to run for the hills because you're worried about quantum computers breaking crypto, feel free to do it, but I'll still be here when you get back.
For a sense of scale, the sorts of systems that are available now are in the dozens of qubits.
Right. Think 50 to 100 qubits for the next several years. They'll teach us a huge amount about how best to get qubits to work together, how they behave given the certain different types of gates that can be applied to them. Frankly, one of the most important reasons to get quantum computing out there right now is I think in 30 to 40 years, all of our technologies will be very quantum. I mean, right now, if you look at how quantum mechanics is used to model transistors, all of the quantum in your phone or your laptop or your tablet, all that quantum has been abstracted away so that the engineers who design the circuits don't have to know anything about quantum mechanics to be successful and have great careers. But I think that in 30 to 40 years, electrical engineers will have to know quantum mechanics in order to design circuits. And so having quantum computing arise in the public consciousness now, I hope will mean that more engineers will learn about quantum systems in school. And in 30 years, when everything is quantum, in my opinion, I'm 60, I'll be 90 then, and by then, of course, my life will be extended because quantum computers will find new meds to do that. The folks who are making investment decisions about technologies and enterprise-class companies will have the background to make the best investment decisions they can about quantum technologies. And so, to be honest with you, one of the things about quantum technology right now that I find so exciting is that it's preparing the next generation to make really, really good, wise investments in technologies that we can only guess at right now.
Ariane Rüdiger, freelancer from Germany. Given what you said about quantum computing or the stage it's now in, which is very experimental still, and you have this tremendous use of energy, and we have an energy problem right now. So the only way I can see that being distributed or used is like we do high performance computing for about 2 or 3 decades now, meaning you have somewhere a center which has the technological design, making able to have that deep temperatures and all that you need. and where you send whatever you have to send there, which is your oven in a way. You put that stuff into the oven and hope the right thing comes out, you know. So can you ever see it as, given that temperature thing, and I don't think there's any way around that because it's pure physics, can you see it being installed close to you? I don't see that.
Well, I don't see it in the next 5 or 10 years, but I think that it's going to have to be like a supercomputer facility. But let's, you know, I realize I am here saying, no, we don't really have to wait for quantum computers to solve problems that are of interest to enterprise class customers. But let's not sell quantum computing short, because I hope and I can believe that in 5 or 10 years, we'll have enough qubits available that we can start trying to solve problems like, to your exact point, to come up with a better solar cell material, for example. There are, again, if the problem is really simple to state, very simple, and it has a simple answer, what's the ground state of this molecule is a classic physics quantum question, then that is just tailor-made for a quantum computer. And so maybe 5 years is too soon, but I hope very much that within 10 years, we are looking at more efficient materials for solar cells and or batteries, and that quantum computing will in fact help us solve problems like that. But until then, it is going to be very much the quantum computer will be in a place that is not close to you, and you will want network access to it in order to ask it simple questions that are profoundly complicated to answer, but then have a simple answer. And so I think that you're exactly right. For the foreseeable future, it's going to be centralized the way a supercomputer is now centralized, and I don't see it being in your phone anytime soon.
I think we have time for one more question. All right, in the absence of questions that are coming to mind right now, Ray, how can people find out more about this and in particular get in touch with you to ask you the questions that they come up with later today?
Ray.Beausoleil at hpe.com. I'll be happy to answer your questions. We have on the HPE website, there are links that can be made available to you so you can learn more about the dot product engine, you can learn more about our optical computing accelerator. Those things are very simple to find, and our comms people know where that information is.
Great. Well, thank you very much, Ray. It's
Certainly.
been great having a chat, and thank you all for joining us.